Hi guys, I'm trying to do a short video about the solar BMS now that the Kickstarter project has ended and is successfully funded. I can give a bit more details about the project, about the hardware and the software, since it's now an open source project. This is the project activity page. I think it's called the dashboard, yeah. And as you can see, it was founded 122%. So I didn't have a very high target. It was only $8,000 Canadian dollars. So yeah, I was hoping for more, like 200-300% at least. But yeah, I knew from the beginning this is a niche product, and maybe it's a bit early for solar BMS at this moment, but I wanted to do it now. I need also this this product, so to speak, for my off-grid house. So I didn't want to wait more for this to be a more popular product. Anyway, I will try to answer quite a variety of questions on this video, hoping though I will keep it short. So let's start with this diagram that I made just now. I should have made it probably before, but I had the impression that most people will understand how this will be connected to the rest of the system, the solar BMS, but I think I was wrong. So at least I made now this diagram explaining how this is connected to battery and solar panels and so on. As you can see here, I have 4 solar panels because this solar BMS can accept up to 1000 watts. So you can think of these 4 panels like being 4 250 watt solar panels or something like that. This is what I would recommend with 8 lithium iron phosphate cells. So meaning 60 cells solar panels, because this will give you the best performance, meaning the maximum power point voltage is very close to the battery bank voltage, so you get the most out of it. You can also use 72 cells. Most people asked about that, but about 2 years ago when I got my panels, the 72 cells were way more expensive than the 60 cells panels, because the 60 cells panels are made for grid tie systems, and these are way more popular. I mean, there's a really high volume production compared to off-grid panels like the 72 cells or 36 cells for the 12 volt batteries, and these were way less expensive per watt than the 72 cells. But right now I think they also make 72 cells for grid tie connections, so I think the prices are now similar, but I still recommend the 60 cells because they will perform better without an MPPT controller. And yes, the solar BMS doesn't have an MPPT included. I mean, for those that know what an MPPT charger is, the difference is not just in software. It's not just a MPPT algorithm, but is also the DC-DC converter, and that will have made this device look way bigger. This is just 200 gram and very thin, like it's 15 millimeter thick, and it's hard to say from a picture what the size of the unit is, but of course here is not on a scale. It's the inverter and the panels are way bigger than this charger, but as I will maybe talk a bit later about this MPPT, it's not an economic. I mean, it's an obsolete technology in my view. It's not economical to build in an MPPT inside a charge controller. It will be too expensive compared to the solar PV panel prices in today's market. I mean, it's even after it's probably even under $1 per watt at this moment. So at this sort of price, MPPT doesn't make any sense. I mean, it will be way more expensive to have an MPPT than just add some maybe 15% more PV panels. So that's it. Now, as you can see, you will need to have fuses. That's the symbol here for fuses, because I use multiple connection points for each connection for load, for battery, and for PV panels. So that the reason to do that, it's not just one, there are many reasons, but one of the reasons was to keep this small and to be able to have the connectors on a PCB. Otherwise I will have needed to use wires and a much larger case, and it will not have worked as nicely as this one. So in order to use this at full capacity, 80 amps and 40 amps for charging, you will need to use fuses on each individual connector. As you can see, the main ground connection, it's outside the solar BMS, so the solar BMS doesn't have access to ground on this power connector. It has access to ground, of course, because he needs his own internal power, but it's only through the measurement connector. And you see these green wires are the 10 wires from the monitor and measurement connector and the balancing connector. And I think the diagram is self-evident, but you have the load that it's connected to these four power connectors, and the load can be anything. I used here a power inverter is the one that I use on my off-grid house, but it can be anything. It can be the power inverter or a DC motor or LED light or anything like that, or multiple loads, as long as they don't exceed 80 amps can be used. And I think, I'm not sure how visible is this in this diagram, but these are 8 individual cells. They look like D-cell batteries or something like that, but they can have any shape. It's not important. I use this because maybe it looks a bit clearer. So you have them in series. You can have in parallel as many cells as you want. That's not an important thing. And then you have you need to have 9 connections in order to be able to measure each individual cell voltage. So you have one on the plus, one on the minus of the battery bank, and then you have 7 connections between cells in between. And I know this connector has 10 pins, but the pin 1 and 2, it's the same as the ground pin, and they are connected together and go to the ground of the battery bank. So I don't know what else to say about this. You can split the solar array in 2 if you want, and then have half of the array on one connector and the other half on the other. But and then maybe you don't need the fuses anymore, but you will probably still use some fuses, even if they are just for panel disconnect or something like that. Anyway, I I think that's it about this diagram. I think it's self-explanatory. Okay, next. Yeah, next I wanted to talk about the way lithium iron phosphate is charged compared to lead acid, because many people had a lot of questions about this and asked me about the PVM and how do I reduce the current and in the saturation charge and this kind of stuff. But lithium ion, it has quite a different charge characteristic than lead acid, and they really need a totally different way of charging. This is a typical charge of an lithium ion battery. It's the lithium cobalt chemistry that it's most used in cell phones and laptops, tablets, all kind of portable devices, and even in electric cars, those that are built by large manufacturers and not by do-it-yourself kind of people. And then in this situation, what it's important for them is the capacity and not the life cycle of the battery. I mean, a 3-year life for a laptop or a tablet or a phone, it's really more than enough. It's what most people expect from a device like that. And then battery life, it's not important above this 3 years. But when you do stationary energy storage, then you are thinking more in the 15 to 20 years life, not just 3 years. And so the charging will need to be different, and I will explain why. So like in a laptop or in a phone, the way the battery is charged, a lithium ion battery, you have a first stage that it's constant current charge, and after that you have a saturation charge where the voltage is kept at depends, like for lithium cobalt, for example, it's 4.2 volts. This is what it's mostly used in laptop or phones. So it will be a constant voltage stage, and stage 2, and the current will drop slowly, and when the current reaches a certain level, this can be discussed, but usually 10% or 5% of the charge current, then, or not the charge current, the battery capacity, then the charge will stop. And then but this second part, the saturation charge, is actually affecting the battery life cycle. It will gain like 15% more energy if you use this second stage of charging, but will drastically affect battery life. And in a stationary, or even not stationary, it depends how you look at it. Even for the electric vehicle, maybe it will be important not to use this part during charging, but this I think most electric vehicle manufacturer use this part because they want to get the highest range possible. So sometimes maybe they limit the charge only to 85%, meaning they use only this constant current charge, and then a battery will the charging will be easier on the battery, and battery will last longer. But when you really need those 15%, then you will use the stage 2. But I think I have here. Look on this website. I need to zoom in for you to be able to read this. But I will have the link of this website on the video description, so you can go there and read everything, but like you see here, lithium ion doesn't need to be fully charged, as is the case with lead acid, nor is desirable to do so. In fact, it is better not to fully charge because high voltage stresses the battery. Choosing a lower voltage threshold or eliminating the saturation charge altogether prolongs battery life, but this reduces the runtime, meaning the available capacity. So you can see here how much if you use only the first constant current charging, the first stage, you only get, if you stop at 4.2, this is a charging voltage for the lithium cobalt chemistry, you get only 85% of the full capacity. So you don't get a full 100%, but the increase in cycle life can be significant. In fact, I've seen in on another study, not sure if it was on this same webpage, I don't think so, but maybe, with each 100 millivolt decrease in charge voltage, you will double the battery life. And so somewhere at 3.9 volt will be ideal. Then you get about 8 times the life cycle on a lithium cobalt chemistry. I mean, I will probably recommend using lithium iron for energy storage. This is what I use, and it's a much safer chemistry. It is heavier, has lower energy density than lithium cobalt, but for stationary energy storage, this is really not important. So, and another fact, the lithium iron at 3.6, that's the what most manufacturers specified in their specification as the maximum charge voltage. If you charge them at 3.6 and stop after the first stage, you get 95% of the capacity. They charge a bit different, I mean quite a bit different from lithium cobalt chemistry. So there you lose only 5% of the capacity written on the battery, so it's really almost nothing, and you increase the battery cycle life quite a bit. So it makes no sense for the last 5% to increase the complexity of the charger and also reduce the battery life. That it's very important in energy storage. If you want to have a good price for amount of energy used from that battery during the lifetime, you want to get as many cycles out of that battery as it's possible. So it really makes no sense for the last 5% to lose that, and not even for not for an stationary application, but even for an electric car. I will suggest you use only that part of the charging and forget about that 5% that will maybe be just, I don't know, 5 kilometers or 10 or whatever your DIY car will be able to go. It makes no sense to reduce the battery life for those 5%, even in that case, or an electric bicycle or things like that. Anyway, I think this is what I wanted to say about the way the lithium iron battery is charged for energy storage. So you only have constant current, but what constant current means is it doesn't mean you have a charger that needs to provide constant, I don't know, 1 amp or 10 amps or something like that for the whole duration of this charging. It can vary. I mean, if you use a solar panel, the current will be limited by the amount of sun hitting the solar panel. So it can be 100%, I mean, I don't know, 30 or 40 amps from the solar panels. and it can be 10%, like maybe only 4, and then maybe you have a cloud and for a few minutes you have less current. This is still constant current charge, because the battery voltage, it's increasing during charge, and the current level, it's not important. You will still call it constant current even if it fluctuates with amount of sunshine. So the battery life will not be affected or anything like that. Okay, I think this is it about battery charging. I should go next because I spent quite a bit of time here. And what's next? Yeah. Okay, this is the AS7620. This is the DC-DC converter that I use inside the solar BMS. It's a 12 pin QFN package. You probably seen it in on the main PCB. And what this one does is help keeping the self power consumption of the solar BMS to a very low level. I mean, look at this, it's just 30 microamps idle current or bias current, however you want to call it. So this is a really great small DC-DC converter. It is a bit expensive, but it's a few dollars, quite a few. I don't remember exactly the price, but it's not cheap, especially when you compare with a linear regulator. But using a linear regulator to when most of the electronics use only 3 volt and your battery is 24 volt, it will be a really bad idea. The self-consumption will be quite a few times higher, maybe even an order of magnitude almost at 24, 28 volt when you only need 3 volt. So this is necessary. I don't want to enter in details. I want to keep this video short, but if you want to see more details, go check this one. Maybe you want to use it in your own project, or this is a really nice DC-DC converter. Okay, next. Okay, I already mentioned this on the on some comments, I think, on the Kickstarter page, but probably most of you didn't read that. This is the main battery IC that I use in the solar BMS. It's from Intersil, and this does most of the thing related to battery. I mean, controlling the FETs and monitoring the battery, taking care of thresholds, all the thresholds. It has some RAM and EEPROM inside, so it's programmable. And yeah, you should also check this the specification for this if you are interested in the solar BMS or something like you want to build something like that. Now that it's open source, I can talk about this. I was not able to say anything about this before, but yeah, I think this is probably the best I was able to find. It was not available at the time I was starting designing the solar BMS. Only the specification was available, but this was not yet in production. And I was probably one of the first to buy samples directly from Intersil. And now it's available everywhere. It's a bit expensive, but if you want to build with something else, all the functionality of this IC, you will not be able to do it cheaper than that. So it's better to have all these integrated in a single chip, even if it's it's not that great because it is a very small QFN package. Let me see if I can get the page with the look. It's a really small QFN package with only 0.4 millimeter pitch. So this is really bad for DIY soldering, and I know a few of my backers took just a kit and they want to solder this, but it will be a challenge, mostly because of this guy. They don't have it in any other format, just this really small QFN. So yeah, this is the challenge with the miniaturization of everything. But other than that, this is a really great chip. It has all the functionality you will want to have. I mean, if I would have designed this myself, I don't think I would have added anything else. So I think that's it about this one. Let's see what else. Okay, the microcontroller that I'm using right now, it's from ST. It's an Cortex M0, and I just found out today that they will they have a new product that I think it will be compatible with this at least the pinout should be the same, and maybe they added one or two things, maybe some more timers or something like that, but it should be really compatible with this. And what's nice about that one, that's the F071. It's not available right now, but I hope it will be before I start production of this solar BMS. And then I will that one has 128 kilobyte of flash, and like I mentioned, I think before, 64, it's a bit of a stretch. I mean, I can implement everything that I said I will implement in the Kickstarter page, but there is also the micro SD card and serial port that I said I will not implement if I don't get to the stretch goals. But at least I want to have a microcontroller here, so that if in the future I have time, or I get time to do more, or someone else want to do it, it will be enough flash memory to easily integrate a FAT file system to be able to write on a micro SD card. So, and that one also has more RAM, which I don't think it is really necessary. I mean, 8K will have been enough for the micro SD. I think you need 4K for the buffer, but I'm not sure. I didn't enter in too many details about the micro SD card, and I never had a project where I needed to write using FAT file system on micro SD card, but so I don't think it will be much more expensive than this one. Maybe, I don't know, $1 or $2, or I don't know. I hope it's very close in price with this. Price is not really that important, since this is not really a for-profit project. So if that will be available before production, I will include the F071. I hope it will. So okay, this is the MOSFET that I use. I mean, I use multiple MOSFETs for load and for the charging part, and for load I use 4 of these in parallel. So you see they have a typical 1.9 milliohm RDS on. So with 4 in parallel I get 0.5 milliohm, or around that point. So the power drop on this 4 will be just around 3 watt or 3.2 watt. So it's like just very small power will be lost on these MOSFETs, meaning that I don't need to have a big heat sink and I mean, 3 watt can be easily and fundless be dissipated by a small heatsink. And in case I will have used an MPPT like I mentioned before, this solar BMS, it's 200 gram. The MPPT version should have been at least 10 times more, about 2 kilograms, because of the inductor, the electrolytic capacitors, and a much larger heatsink, much larger. I mean, even a very efficient DC-DC converter used in MPPT controllers is around maybe 95-96% efficient at 100% load, meaning that for 1000 watt of solar panels you lose something like 40 or 50 watt. That's more than 10-15 times more than I dissipate now in heat. So you'll have needed a way larger heatsink, or maybe active cooling with a fan or something like that. But I don't think many people want to have a noisy charger that makes noise all the time, or at least during the day when you do the charging or something like that. So if you want a funless one, you will need it with a large heatsink, and not only it will be heavy, it will be more expensive. And that's just a heatsink, but you have the electrolytic capacitors that will need to work in that heat. So even a few degrees more will short considerably the life of the electrolytic capacitors, and then you will need to buy a new MPPT controller every few years. If you want me to talk more about implication of the low-cost solar PV panels in many areas, not just the MPPT. MPPT is one of the obsolete technologies because of the cost of solar PV, but also solar tracking is in the same situation, and many other technology used in the past for when the solar PV was probably $10 or more, and was not very long ago. That's why I mean, things move so fast, people don't really have time to understand what are the implications and what sort of technology used before died because of this. Even how do you call that? The thermal solar. In my mind, thermal solar is also dead because of the PV. You can use just a resistor and heat water or whatever you want to heat with the solar thermal, and it will be less expensive. I can make a calculation showing that, because I was investigating that for my off-grid house, and it's just crazy. At $1 per watt, solar PV will be cheaper than direct thermal solar variants available, especially in cold climate where you can only use evacuated tubes. Those are not that cheap and not very reliable, and then you need pipes, and you need water pumps, quite expensive water pumps that work with hot water, and you need to insulate the pipes, and all that complication is even if you don't take that in consideration, solar thermal is expensive. But yeah, if you want, I can make a separate video about that. I don't want to enter in too much detail about this right now. Okay, this is the schematic. It's just for the main PCB, just a schematic for the main PCB. I have 3 PCBs in this solar BMS, but anyway, this contains most of the components. So as you see, it's split here in 5 regions. This one here is the LCD and micro SD card, and this is microcontroller, and then this is the power supply. This is the BMS IC, the battery IC, with whatever is around that one. And then this part here is just a connector for connecting the three PCBs, and this is the 10 pin connector for battery monitoring. Then this one is the opto insulated part, those two opto insulator. I will make this available, this schematic available, but I just need to make some changes. It makes no sense to make it available now and then maybe someone will use this as a reference and it will be wrong, because I have a little bit of changes to do in here, and then I can show you more. Okay, and this is the PCB. Again, I have some changes to make here, and then I will make this available. And also I need to add the open source logo, and I'm not yet even sure what sort of open source license I will use here. I mean, with software it's a bit easier. I will probably use GPL or LGPL, but for this one I don't know exactly. I will need to check a little bit more, because this is my first open source project, and yeah, I need to check about the licensing. Okay, so this is the software. It's quite a mess. I'm not really an organized guy, especially when it comes to software, but I want to clean this and make it more organized. But there is a lot of stuff in the main file, and it will take me too long to go through everything in here, but I will try to clean everything and have it licensed under GPL or something and upload it somewhere. And you can take a look, and if you have any suggestions or ways to improve this, I'm really happy to take a look and update this. And yeah, I don't think I will go into any details right now, but what I want to do first is to finalize the testing on the beta sample. So I know all the hardware changes that need to be implemented in the next sample, because I will build another sample before production, sort of pre-production sample. Hopefully that one will not need any more changes, at least not in hardware. Software, it's much easier to do. And then once I have done that part and make that available as open source, then I will check the software and make it also available immediately after I will release the hardware. So I hope no one is too impatient or wants to see this before that. If you really want the software or the hardware files, just contact me. I will send you these temporary ones, but you'll probably not like it. They are not very well organized at this moment, but I will arrange everything and it should look quite a bit better. I'm the sort of guy that just throws things and wants to see that works, and then if it has time it will arrange everything. But since this is it's not just my project, it's now I have, I think, 58 backers or something. I will try to be more organized and have this in a much nicer form. Okay, I think this is all I wanted to say in this video. I will try to make update videos as often as possible. Every time I have something new done to show you. I will try to make a short video and show you that. I know this will be just for a small group of people, probably, like my backers and maybe a few more others. So I apologize to my subscribers that in the next few months there will be a lot of solar BMS videos and probably not much more else. I have a video about the wind turbine that I want to make. It's not really a review, but I have some footage and it's already edited. I just need to make an audio for that one, and then I will upload that maybe next week or something like that. Anyway, thanks for watching, and if you have any questions, please leave a comment and I will try to answer if I can answer.